We're continuing on with Unit 10, Part 2. In this section, we're going to discuss selected serological procedures that can be used to assist in antibody identification. I call these the other tools in our toolkit in the transfusion service. So when a pattern fails to indicate a specificity, we can utilize a number of other procedures. And you need to memorize and know the minimal information about each of the following that we're going to discuss. Enzyme techniques are one of the most frequently used in the transfusion service when we're having difficulty with identification of an alloantibody. Treatment of reagent red cells with enzymes removes the sialic acid residues on the cells, making some antigens more prominent or accessible. So treatment of red cells with proteolytic enzymes enhances reactivity of RHPI Lewis and complement binding alloantibodies such as anti-JKA. So it assists them in overcoming the zeta potential where the antibodies can actually attach more heavily, and the increased coating enhances the strength of the reaction. On the flip side, antigens of the MNS and Duffy are either depressed or destroyed. The antibody cannot react. And you may, for example, let's say you have multiple antibodies and one of them's a Duffy. The Duffy in a regular panel may be 4+. On a Fison panel, it may be 1+. So sometimes if the strength of the reaction is very, very strong, the antibody can still react. But for the horses versus unicorns, think that those antigens are destroyed, and so the antibody cannot attach to them. Enzyme techniques are used whenever weakly reactive antibodies may be an Rh antibody, or when a patient has multiple antibodies and one of them is a Duffy. Temperature reduction is very useful for alloantibodies such as anti-M, anti-P1 that react better at cold temperatures. The specificity may become apparent at or below 22 degrees centigrade. 22 degrees centigrade is room temperature. And autocontrol is especially important for tests at cold temperatures because many sera contain cold reactive autoantibodies. In fact, the majority, if we ran cold panels on everybody, all normal people, a lot of people will have naturally occurring autoantibodies that react at 4 degrees. Anti-Big I specificity is confirmed by testing patient serum with adult, which are I positive, and cord, which are little I positive cells at 4 degrees. The expectation is positives with the adult cells and negative or very, very weakly reactions with the cord cells. And this is done to confirm anti-Big I specificity. And again, an autocontrol must be run, and the expectation in this situation is that it will be positive because you're a normal adult. You will have Big I antigen on your cells, and they will react with the antibody. Another tool is to increase the serum plasma to cell ratio. This increases the amount of antibody in the test system, which may increase the strength of reactivity of antibodies that are present in low concentrations. And remember, our immune system is very, very good, but some people over time, the antibody levels will decrease in titer, and it may be to the point that it's below the level of detectability. You can increase the serum to cell ratio by 4 drops or more. You may have to add additional washes because what's in the serum or plasma? Protein. What will cause neutralization of your Coombs serum? Protein. So whenever you increase the amount of plasma or serum, I always add an additional wash. List requires equal volumes of serum and RBCs. Now keep in mind, you don't have to use an additive, and especially when you're doing an increased serum to cell ratio, if you want to use 4, 5, 6 drops of serum and the 1 drop of cells, that enough, the protein in that serum or plasma may be a potentiator. It may enhance the uptake of antibody on the cell. So again, follow the manufacturer's instructions of your additive solutions. You cannot deviate from those procedures. Increase the incubation time. When no additive is present, you can use 30 to 60 minutes to allow more time for more antibody to attach to the red cells. And this is used in conjunction with increasing the serum to cell ratio, increase the incubation time, so you have more antibody and you're allowing more antibody more time to attach to those antigens, and I guarantee you this will increase the strength of reaction by a minimum of 1+. What's very important to note is you do not exceed the incubation time recommended by the enhancement media manufacturer or your standard operating procedure manual. Most manufacturers, for example for LIS, I believe the maximum is 20 minutes. So be very careful that you always follow the SOP. For anti-Ms, decreasing the pH is an excellent tool. You want to decrease the pH to 6.5 by the addition of 0.2 normal hydrochloric acid. I want you to memorize that. Weak anti-Ms are greatly enhanced, and I told you my story. It went from a 1+ to a 4+. It was amazing. To enhance or increase the strength of reaction, maybe change your enhancement media. Low ionic strength saline solutions, some blood group antibodies react preferentially in test systems utilizing LIS, and a variety of LIS procedures have been described, and there's a variety of reagents by different manufacturers available. Polyethylene glycol, PEG, many transfusion services are now using this as the primary enhancement reagent. Not all over the United States yet, but in many large transfusion services. It is not read at 37. So getting yourself out of that routine of, spin, read, record, immediate spin, incubate, spin, read, record, 37, wash. It just, to eliminate that spin after the incubation is something very difficult. But once you use it, you develop your routine and you know not to read it. Because if you do, spinning after incubation may cause irreversible pseudoagglutination, a false positive. And after doing that a couple times and having to repeat the procedure from scratch, the memory mark is made. Thiol reagents are really cool. They dissolve disulfide bonds between cysteine amino acids, potentially affecting both red cell antigens and antibodies. But we're specifically going to talk about antibodies. Some strong IgM class antibodies may have high thermal amplitude. They bind so strongly at room temperature that at 37 they don't want to let go. And because they have not let go at 37, then you'll get a false positive at Coombs. And how you know this is when you're doing your washing. You spin and you agitate to break up the cell button. The cell button won't break up because the cells are already agglutinated. But you must go on to Coombs. Anyway, because of this, again, very rare example of an IgM antibody showing high thermal amplitude, this may mask or cover up other alloantibodies. So we want to get rid of the reactivity of the IgM antibody. There are two reagents available, dithiothiazole DTT and 2-mercaptoethanol 2-ME. Both of them do the same thing. They cleave the intersubunit disulfide bonds of IgM molecules. The IgG molecules are relatively resistant to cleavage, so the treatment results in the destruction of the IgM antibodies, and it doesn't matter what specificity. It doesn't say, oh, we're going to get rid of this anti-M IgM. No, it's all IgM antibodies, but it leaves the IgG intact and able to react in vitro. So you've done your testing, you have demonstrated the strong thermal amplitude, you've identified the antibody. You always have to do all these other things first before you try a thiol reagent. Then you add the thiol reagent, and what will happen is the IgM class antibody, it can't react because it's been destroyed, the IgM antibody. And so if an IgG is there, you'll be able to see it. There are 3 applications that I want you to memorize. Determining the immunoglobulin class of an antibody, especially if the antibody has potential to cause hemolytic disease of the fetus and newborn. dissociating red cell agglutinates caused by IgM antibodies, for example, spontaneous agglutination of red cells caused by a potent cold reactive autoantibody. So you've done your testing, then go ahead and treat the serum or plasma, retest, and if this was truly the case of an IgM, then you'll be able to see that go away. And then finally, identifying specificities in a mixture of IgM and IgG antibodies, particularly when an agglutinating IgM antibody masks the presence of IgG. Pre-warm technique, I believe this is the third time we are discussing this. Cold autoagglutinins may demonstrate high thermal amplitude, and again, I will define high thermal amplitude. It binds so strongly at room temperature, it does not want to let go at 37. It's an IgM, but again, because of the uniqueness of this particular alloantibody, it just keeps stuck. So this results in false positive reactions at 37 and Coombs. A pre-warm technique can only be done after antibody identification is performed and anti-Big I is identified. And some transfusion services don't even allow this procedure to be done because it really takes a great deal of expertise of knowing what you're doing and when to do it so that you're not accidentally missing a clinically significant antibody. So a pre-warm technique can confirm that only a cold autoagglutinin is present or detect the presence of clinically significant underlying alloantibodies, ones that were hidden or masked or covered up by that primary cold antibody. Once again, I want you to memorize this procedure. So how you do it is you place the red cells to be tested in appropriate test tubes. So I label my tubes S1, S2, and S3, and I put those in the heat block. Then I pre-warm a tube of serum at 37 degrees. So I just take my sample, my patient labeled sample, and put it in the heat block. Then this only takes a few minutes, and I always make sure the volume of the serum or plasma is below the heat block level so that there's none on top, which may be cooled. So then once it's pre-warmed, you add 3 to 4 drops of the pre-warmed serum to the pre-warmed cells and incubate 1 hour. The reason we're incubating for 1 hour is we are not adding a potentiator, an additive. Potentiators will enhance or increase the reactivity of cold antibodies. So we're doing this with a simple serum cell test. Without removing the tubes from the heat block, you add saline that has been pre-warmed to 37, and you document. I've told you I take a clean squirt bottle, I fill it with new saline, I put it in the microwave, and I can't remember how I finally determined the magic amount of time, but you don't want to overheat or underheat. So once you put a thermometer in there, verify the temperature, and then you add, while those tubes are in the heat block, the pre-warmed saline to the pre-warmed mixture. Then remove, immediately spin down, and continue washing as necessary to go to Coombs. Inhibition tests are very useful. Some blood group antigens exist in soluble form in such body fluids as saliva, urine, or plasma. These substances are useful in antibody identification studies, either to confirm antibody specificity by inhibition or to neutralize antibodies that mask the presence of concomitant non-neutralizable antibodies. What does that mean? So we have two antibodies present. One can be neutralized, so we add the substance, and that will just leave the other antibody all by its lonesome, easy to identify. The following soluble blood group substances can be used in antibody identification tests: Lewis, P1, and SDA, also known as SID-A. Lewis inhibition tests are discussed first. So Lewis A and Lewis B substances are present in the saliva of persons with appropriate Lewis phenotype. Lewis substances can be prepared from saliva, and most blood banks use commercially prepared Lewis substance. You don't want to find out what your Lewis phenotypes of your colleagues are, and then take the saliva and, no. Just, it comes in a bottle, just buy it. Most Lewis substance will neutralize Lewis antibodies in a patient's specimen, allowing the detection of the underlying clinically significant alloantibodies. And you have to run these in duplicate, and I talked about this before. So you have your untreated serum or plasma, which is not neutralized, and then your neutralized, and you compare them side by side. So if it works, the Lewis will be present in your original sample, and then the activity will go away in the treated sample. P1 inhibition test, I want you to know soluble P1 substance is present in hydatid cyst fluid as well as pigeon eggs. Anti-P1 may mask the presence of underlying alloantibodies if they react very strongly and they have high thermal amplitude. Addition of P1 substance to the patient's serum causes neutralization of the P1 antibody, means it goes away, and it allows the detection of underlying alloantibodies. And I can't say this enough. These little tools in our toolbox, these are done after the complete initial workup is performed. SID-A inhibition. SID-A blood group substance is present in soluble forms in various body fluids, with the most abundant source being urine. So urine from an SDA positive individual is added to the patient's serum. We use a recipe, we just don't guess, and it causes neutralization of the anti-SID-A antibodies. So this aids in the detection of underlying alloantibodies. And if you remember, SDA has that mixed field agglutination appearance. And in my first job, we somehow determined that our lab director, she had SDA substance in her urine. And so anytime we had a SID-A antibody, we'd go ask her to pee in a cup. And then we had a procedure for how to use that. In modern day times, this would not be allowed because you have to validate that, everything that she was SDA negative with the SDA positive with this substance in her urine. And so, again, commercial stuff is available. But hey, what's cheaper than taking a cup and asking your lab director to urinate in it? Titrations are usually done in reference laboratories because you need to have individuals who do these on a regular basis and who are able to maintain competence and demonstrate competence. In transfusion service, with the exception of HTLA antibodies, we generally don't do them. A titer of an antibody is usually determined by testing serial two-fold dilutions of the serum against selected red cell samples. This is why we had you do serial dilution so many times in your serology labs, because it is the most frequent procedure done in serology so far as titers are concerned. So we have a 1 to 10, 1 to 100, or whatever, but it's a doubling dilution. If it's 10, 100, 1,000, 2, 4, 8. So you test you dilute out the patient's sample, and then you test it. The results are expressed as the reciprocal of the highest serum dilution causing macroscopic agglutination. So 1 to 10 is the dilution, the titer is 10. And students get this confused. Even out there in the real lab world, I have seen titers reported out as 1 to 10, and it just makes me cringe. We're going to talk about 3 applications of titration studies, and that's prenatal studies, antibody identification, and HTLA antibodies. Titration in prenatal studies. If an antibody is of a specificity known to cause HDFN, or when the clinical significance of this particular antibody is unknown, the results of titration studies and outcomes of previous pregnancies are used to assess the need for amniocentesis. So what that means is, what if this mom had an antibody stimulated by a previous pregnancy? So that baby was affected. How do we know that this antibody presence is going to affect the current pregnancy? So what we do is rising titers are indicative of the fetus possessing the antigen to which the mother has an antibody. and indicates a potential need for amniocentesis. We talked about amniocentesis in body fluids, and we will talk about it again when we get to the section called babies and mothers. And it's an invasive procedure that is not without risk. So by doing these titers, we can determine which ones may need it and which ones may not. If there is no change in titer, this indicates that the fetus lacks the offending antigen, so there's no need for an amniocentesis. So again, a previous pregnancy may have stimulated this antibody, and this particular fetus does not have the antigen, so the titer will not go up. Titration for antibody identification. Some antibodies cause agglutination of virtually all reagent red cell samples, but specificity is indicated by the differences in the strengths of reactivity with each sample in the titration studies. So what you do is you dilute the serum and perform the procedure according to the SOP. You test the diluted serum against a panel and look at the remaining reactions to determine specificity. So if we have varying reactions, and one was a 1 plus and one was a 4 plus, by diluting it, the 1 pluses may go away and the dilution will cause 3 plus. So it's a single dilution of the sample that you test against the panel cells. This titration procedure is not used very commonly for this purpose. I personally have never used it, but just know that this is a potential application of this technique. Another application of titration is for high titer, low avidity antibodies, also known as HTLA. HTLA antibodies react very weakly in undiluted states, but unlike most weakly reactive antibodies, for example, an anti-D with a titer of 4, these HTLA antibodies react at the same strength when highly diluted, for example, 1 in 2,000. And they're plus minus. They're plus minus when you test them with regular serum, and then no matter how far out you dilute it, I'm sure there's a limitation for how far out, but at an incredibly high dilution, these will still react plus minus. And that's why they're called high titer. There's a whole bunch of them, but low avidity, because apparently the reaction is very, very fluid, and they're coming off and coming on at the same time. To remember, there's avidity and affinity. There's just not much, there's affinity, but there's not much avidity. They're not able to stick on. Such antibodies include there's Chido, Rogers, the rest of them. I don't want you to memorize the specificities, but I do want you to recognize or say what HTLA is, define them, and state how helpful a titration is working these up. When weak reactions are observed in the indirect antiglobulin test, titration studies may be used to establish whether the reactions are due to the presence of an HTLA antibody. And most transfusion services, the busy ones, will do this when a HTLA is suspected. Adsorption. In blood banking, adsorption refers primarily to the adherence of an antibody or antigen onto the surface of a red cell, and is described briefly below and in more detail during the discussion of autoimmune hemolytic anemias. So antibodies can be removed from a serum by adsorption to red cells carrying this corresponding antigen. So what we do is we incubate this serum with an antigen positive cell. So you would look at like I said, we save our expired cells. We would look for the antigen to the antibody that we want to get rid of. And so we would wash that cell suspension, add the patient's serum, and then incubate. The antibody that's present forms a complex with the red cell membrane-bound antigens, and when the serum and RBCs are separated, the antibody remains attached to the red cells. So subsequent elution or removal of that bound antibody can often give additional useful information. So I provided a link here to the Blood Bank Guide discussion on this topic that I believe you will find useful. So adsorption, again, is the removal of an antibody by incubating the serum that contains the antibody with an antibody-positive cell. The antibody will then bind and be removed. There's different applications of adsorption, and we talked about adsorbing out an alloantibody. And in this case, this is called an autoabsorption, where we take patient cells that you can see have autoantibody coating them, and in the background we have an alloantibody. So we go do an autoabsorption to remove the cold antibody because it's masking or covering up an alloantibody we want to see. So we'll incubate the patient's serum with the patient's cells at an appropriate temperature. Then we spin it down, we harvest the serum and test that against a panel cell. And the beauty of it is we no longer get the interference from the autoantibody because only alloantibody is remaining. I want you to memorize the 5 uses of adsorption techniques. 1, removing autoantibody activity to permit detection of coexisting alloantibodies. So that's the example I just showed you in the previous slide. Removing unwanted antibody from serum that contains an antibody suitable for reagent use. This would be more on the manufacturing side, so that we have a patient or donor with 2 antibodies and we only want single specificity, so we can select cells with that antigen, incubate that donor plasma, and then harvest the top of the serum and then remove the antibody from the antigens on those cells. Confirming the presence of antigens on red cells through their ability to remove a specific serum antibody. So this is mostly done in weak subgroups of A where the person has the A antigen, but we're getting a negative reaction with anti-A. We can actually incubate that patient's cells with anti-A, wash, and then remove the coated antibody if present, and identify that these truly are A antigen positive. Confirming the specificity of an antibody by showing that it can be absorbed only to red cells of a particular blood group phenotype. So for the example, anti-CE, which is F, we can do an adsorption test to confirm by adsorbing that on to the F positive cells that this is truly an F. Separating multiple antibodies present in a single serum sample. So this, again, in my experience, maybe I've done it one time, but this is more reference lab. So again, the patient has multiple antibodies. You pick cells that are positive for one antigen specificity, negative for the others. And so you have these different aliquots. And so then you incubate the patient's serum with those different aliquots. You can harvest the serum and test. And then you can wash those cells and do a procedure we're going to talk about in a moment, an elution to pop those antibodies off the cells to release them into solution for additional testing. And I know this is really, really high upper level stuff, but I want you to know it. It's important for you to at least know the basics of adsorption techniques and the variety of ways that this technique can be used in blood banking. Elution in general is to remove or extract one material from another. In the blood bank world, the term refers to removing or dissociating an antibody that is attached to the surface of a red blood cell. The elution technique frees antibody molecules from these sensitized cells so the recovered antibody can be tested. There's a variety of methods that are employed with the primary objective being breaking that bond between the antigen and the antibody which is attached to. We used to do these all the time, especially for ABO hemolytic disease of the newborn, because there's a very easy technique that we can do, but these have become more less frequently used. And when we get to that section, I'll talk more about why elutions are not as necessary, except for certain circumstances as before. The use of elution techniques, these go from the most common to the least common. So the most common used to be for identification of an antibody coating a baby's red cells in the case of hemolytic disease of the fetus and newborn. And I talk about baby's blood being two parts. The cells are from the fetus, but the plasma, of course, has the antibodies from the mom. So they're two patients in one. And in hemolytic disease of the fetus and newborn, a maternal alloantibody will cross the placenta and attach to the antigen, if the baby possesses it, on the baby's red cells. And in order to determine what is coating the red cells, we pop those antibodies off and then we test those against a panel of cells. And hopefully the specificity will match the specificity that's in the maternal sample, because that's where the antibody came from. Identification of an antibody causing an acute or delayed hemolytic transfusion reaction. So the patient came in, pre-transfusion testing, no problem. We gave them blood. They come back in for whatever reason, and now their antibody screen is positive and their direct antiglobulin test is positive. So what we need to determine, and the DAT, again, you wash the cells 3 times at Coombs, so these are just cells. But remember, once you transfuse a patient, it's not just the patient anymore. It's however the patient and however many other donors that are mixed in with that patient. So again, an alloantibody can be formed. It will attach to the donor cells because that's why we're making it. So we can go ahead and do an elution procedure, and the antibody that we're recovering comes from the donor cells, not the patient, but the donor. And when we get in delayed transfusion reactions, we will talk about this again. Investigation of a positive direct antiglobulin test for whatever reason. And because we don't do auto controls routinely anymore, we must do them as part of an antibody workup. We rarely do elution procedures for the investigation of the DAT. But when we get into the autoimmune hemolytic anemias, we will talk about why and how those are done. And then this goes into manufacturing, concentration and purification of antibodies, the detection of weakly expressed antigens, and the identification of multiple antibodies. And then lastly, the preparation of antibody-free intact red cells for use in phenotyping or autoabsorption. There are times, especially in cold autos and even warm autos, that we'll need to adsorb out the autoantibody so that we can see if anything is left for the in the serum. But we can also use that elution technique to remove antibodies to free up antigen sites on cells so there's room for more autoantibody to go on. So again, I went through this relatively quickly. Go ahead and spend some time on it, but just know we will come and revisit this again. Technical factors can cause problems when performing an elution. Incorrect technique. You must follow the manufacturer's instructions. And if I haven't said it once, I will say it 1,000 times, because some students think, oh, I can skip that procedure, or I can alter that step, or no, you can't. This is not your world. This is the world of the patient, the world of laboratory, and doing things right. Of all the technical factors that will get in the way the most, incomplete washing. If cells are incompletely washed, contaminating serum antibody will cause false positive reactions. So what we're ultimately wanting to do is free antibody bound to the cell in solution so we can test it. If you do not resuspend those cells adequately between every wash, and you're using 1 ml, 20 drops of cells, then you can get protein, a false positive, due to insufficient washing. Just like in the Coombs test, That won't cause a false positive, it'll cause a false negative. An aliquot of saline from the last wash is saved and tested in parallel. Positive reactions with the last wash invalidates the test. The last wash is your negative control. And I will repeat this story again later on, but I had a patient that she had such a strong auto that I washed her cells the number of times. Then I tested the last wash and the eluate. Her last wash was 4+. Did that have to do with me and my technique? Absolutely not. It's just the titer of her antibody was so incredibly high. It finally got to the point that I got a large plain red. I put the 20 drops of cells in there. I washed it 10 times. And I learned to test my last wash first. I still had a positive last wash control. But at that time, it mattered not. We knew what we were dealing with. Bindings of proteins to glass surfaces, so antibodies are proteins, so that could cause an issue. Dissociation of an antibody before elution. So I want to capture this antibody that's coating the cells, but due to the low avidity, the ability to stay bound, it has come off. Does it matter? I don't know. And instability of eluates. Again, follow your SOP. Eluates can only be used for a specified period of time. So let's summarize the steps. The main purpose of this presentation is that if an unexpected antibody is detected in a patient's serum or plasma, it must be identified. Let's go through the process of how that happens. First, an antibody screen is done. It's positive. Because the antibody screen was positive, you perform a panel, which includes an autocontrol. You must identify the antibody, and you may need to use or perform some of the special testing techniques discussed in this presentation. Once you've identified the antibody, you must determine the clinical significance. For the donor, you will need to phenotype the donor, and if the antibody is clinically significant, you must type it to make sure it is negative for the antigen. If the antibody is considered clinically insignificant, M, N, P, Lewis, I, there is no need to phenotype. But the bottom line is that the donor unit, whether it's phenotyped or not, the Coombs cross-match must be performed and the donor must be compatible. This will prevent errors in which you misidentified the antibody. You called it an anti-Cal when in reality it was an anti-Big E, and your donor has the Big E antigen.